Okay, yeah. So the last exercise we did, we were looking at what happens when you are trying to form an alkyl halide, and we said HCl or HBr only work well for tertiary halides. If you've got a primary or a secondary, you're probably better off with PBr3, PCl3 to avoid rearrangements, because with PBr3 that goes via SN2 reaction. Okay. Now, remember in here, we had done this exercise in which we converted an OH into a tosylate. That does not involve a change at the stereochemical center, because we're just touching a bond over here. We're not changing stereochemistry here. So this was R, this is still R, right? But then once we've converted this into a good leaving group, I can come in with a nucleophile attack from the back. That will invert configuration because this is an SN2 reaction. And then I end up with the opposite stereochemistry. They're starting with R, this is now S, right? Now, tosylate is one type of good leaving group. A bromide ion is another type of good leaving group. So I could certainly put this with, let's say, PBr3 and convert this OH into a bromide ion. Now, what type of reaction is that with PBr3? Right, we talked about the fact that first your OH picks up, kicks out a bromide, right? Let's say. You form this intermediate here. And then this same bromide ion now comes from the back and attacks and gives me a bromide here. But what type of reaction is this attacking from the back in one step? SN2. And of course, an SN2 reaction results in an inversion of configuration. So if this was R, by the time I do this SN2 reaction, this is going to invert these two. I'm now going to have the hydrogen in front and the methyl on the back if everything else is on the same place, right? So I've gone from an R to an S. The easiest way to show an inversion, rather than trying to redraw this and looking at weird stuff, just, if you want an inversion, just flip these two. Replace the OH with the bromine in the same position, but flip these two. And when I flip these two, clearly that is an inversion of configuration. So that's one inversion, where I now have a good leaving group here. Now, if to that, right? I've gone from the R to the S. If now I put sodium cyanide on that, that's going to be a second inversion, because that cyanide ion is now going to come from the back and cause a second inversion. So now we invert these again. And I'm back to the R. So I have two different methods that are on paper the same. Convert the OH into a good leaving group, and then do an SN2 reaction and come from the back and replace that leaving group with another nucleophile. But depending on which one I choose, the stereochemical outcome is different, right? In here, there's only one SN2 reaction, and that's this one. And so this results in a net inversion of configuration. While in here, there are two SN2 reactions. There's one right here to give me the bromide, and a second one right here to substitute the bromide for the cyanide. So that results in two inversions, which basically means that whatever I started with, that's what I'm going to end up with. So I have the option, depending on what stereochemistry I need at the end of the day, which approach I take. And that is what you have. Well, we talked about the phosphorus halides and cyanide chloride, but that is what you have in here. That is, if I were starting with this R2 octanol, and I wanted to end up with an R product to which I'm adding, replacing, what's going to be my leaving group, the OH, for this ether. If I want retention of configuration, I'm going to do two SN2 reactions. That involves converting this into the bromide. That is my first SN2 reaction. And then doing a second SN2 reaction where I come with a strong nucleophile, kick up the bromine from the back, and now go from R to S and from S back to R. Okay? This effectively retains the stereochemistry at the end of the day. If I want to go from the R to the S, then I can only do one inversion, which means I have the OH react with tosyl chloride to form the tosylate. My oxygen is still here. This stereocenter has not changed configuration. If this was R, this is still R. So this gives me a leaving group with the same stereochemistry. This gives me a leaving group with opposite stereochemistry. And once I have this, then same deal, I come in with the ethoxide ion, the strong nucleophile, come from the back, kick this out. So in this case, I only have one SN2 reaction, one inversion, which takes me from R to S. And here I have two SN2 reactions, so my R at the end of the day is still R. So again, if stereochemistry is an issue, then you've got these different approaches to get to different stereochemical outcomes. The general idea is the same. Let's convert the OH, a poor leaving group, into a good leaving group, and then come in with a nucleophile and kick it out. That is the same. But it's just, in this case, there's an inversion here. In this case, there's no inversion. All right. And let's look at problem 8. So problem 7 I just did. Okay, see on problem 5. We just did the opposite approach. But let's look at problem 8 here. So this is a more synthetic problem in which I'm telling you what is the product, and I'm telling you reagents, and asking for what the substrates are at each step. Now, obviously, you're going to look at the product first, and then do some sort of retrosynthetic analysis. So this is hexanol, so 6 carbons with an OH on carbon number 3, and then 3, 4 dimethyl 3-hexanol. All right, now, this product is coming from a Grignard reacting with something. And Grignards, to give you alcohols, are typically react with aldehydes or ketones, something like that. Now, both my Grignard and the aldehyde or ketone or ester or whatever this is, both of them are coming from the same original compound, to which I do different reactions. But what that means is that both of these likely have the same number of carbons that then combine to give me this. So one of the things that I would be looking and figuring out what A is let's chop this down the middle in terms of carbons. Remember when you have an OH, right? This carbon OH forms as a result of a Grignard attacking a carbonyl. But the question is, was the Grignard this one and I formed this bond, or was it this one and I formed this bond, or was it this one and I formed this bond? In this particular case, which one would you most likely choose? Blue, orange, or red? If I want to have both pieces coming from the same compound, if I want both pieces to have the same number of carbons,
Orange.
if I make this bond, this piece with 4 carbons is going to be attacking this piece with 4 carbons. So now I have 2 4-carbon pieces that can be coming from the same original 4-carbon compound A. Now, when I oxidize A with a strong oxidizing agent, I get B. My B is likely a ketone or aldehyde that is going to be attacked by this Grignard. What is B? What ketone or aldehyde is going to be attacked by this Grignard? This, right? This is when the Grignard comes, attacks here, this breaks up. When this breaks up, I form the alkoxide ion, and then when I toss that in, acidic water, I end up with this, right? What is the Grignard? The yellow part, right? This is the Grignard that attacks this ketone to form this bond, right? Now, how did I make that Grignard from what? What is C? We're going backwards. The alkyl halide to which I added the magnesium to form the Grignard, right? So C is this alkyl halide. Now, this alkyl halide was formed from what? To which I added PBr3, or this ketone was formed from what after oxidizing? What do I oxidize to a ketone? A secondary one, right? You cannot oxidize tertiary, but you can oxidize a secondary to a ketone. Or, all right, so this secondary alcohol is either oxidized to this ketone, that would be B, or with PBr3, this gives me this alkyl halide, which in the presence of magnesium forms this Grignard, which then is added to this ketone to form this alkoxide intermediate, right? We have, let's say, right? We just formed the critical bond right here, and then toss that in acidic water, and I'd form the alcohol. So this is what you do with a retrosynthetic analysis. You look at the product. In this case, it's important that both pieces that react together are coming from the same original compound. So that tells you, well, let's split this in 2 equal halves and add the 2 equal halves together. Okay, the 2 equal halves in terms of carbon, because this has the same number of carbons. So I started with 2-butanol. On one end, I put the 2-butanol with PBr3, formed the 2-bromobutane, put the Grignard, put magnesium, formed the Grignard. On another pot, I got 2-butanol and I oxidized it to the ketone. Once this Grignard was formed, I added the ketone, formed this intermediate, hydrolyzed, and then I have the product that I'm looking for. You need to be able to think backwards. I give you the product, and you need to think back. how do you make that product? And certainly Grignards we've looked at a lot. You're adding a Grignard, a nucleophilic carbon, to an aldehyde or ketone, or if you have an ester or acid chloride, you add twice. Okay, and your product is an alcohol. So that's what you need to be thinking of in this retrosynthetic analysis. Right, we all understand that this is on paper. This I had two different pots of 2-butanol. On one I oxidized, the other one I put PBr3, blah, blah, blah. And then eventually I joined them together and that gave me the product. You need to know your reagents, your reactions. You need to be thinking in terms of retrosynthetic analysis. What do we make alcohols from? Well, one very important way of making alcohols is Grignard addition to a carbonyl. So keep that in mind. Okay, particularly if I put in here Grignard, then that's kind of a giveaway of what this reaction is about. Okay. So we were looking at different reactions, and all this chapter is about reactions of alcohols. So we looked at oxidation to form ketones, aldehydes. We looked at converting it to a better leaving group so that I could then do an SN2 reaction, like for example, add hydride ion to reduce it, or a variety of other things. We looked at converting this into a good leaving group, be it the tosylate or the bromide, and then do an SN2 reaction to form, for example, halides. We looked at, or we're going to look now at dehydration reactions. So another reaction of alcohols. This is, of course, an E1 elimination. We looked at back in chapter 7 or thereabouts. So this is, we have some sort of an alcohol. And to do a dehydration, you're going to eliminate a hydrogen and OH, except not OH, right? Because OH is a horrible leaving group. So I need to convert this into a better leaving group. What are the three ways that we know to convert an OH into a better leaving group? Tosylate.
Halides.
Convert it to a halide. And add it to acid, right? If I add this to acid, let me just not put all of this right now. My leaving group is now water, right? If I put potassium chloride, my leaving group is a tosylate. If I put, let's say, PBr3, my leaving group is now a bromide. Okay, these are all converting a poor leaving group into good leaving groups. Now, each of them is going to involve in different reactions, but certainly this is one way of converting a poor leaving group, which would be OH minus, a strong base, into a good leaving group, neutral water, okay? So in chapter 7, we looked at doing that, right? We looked at having an alcohol, which is not going to eliminate, putting it in acid, forming a good leaving group, which then leaves and forms a carbocation. This is an E1 elimination, right, two-step. And then some solvent, whatever comes by and extracts this hydrogen, and at the end of the day, you form an alkene, right? But we need a good leaving group. We're gonna form a carbocation, right? You're looking at this, we form the carbocation, and then your product, right? A two-step reaction.
Susie, what's the first reaction part? I can't tell the yellow highlighted.
OH2 with a positive charge. Right, your oxygen picked up a hydrogen with a positive charge because I put this under acidic condition. Okay, so, and then of course, the fact that you have a carbocation, this puppy can eliminate, it can undergo an SN1 reaction, it can do rearrangements, and then undergo E1 or SN1. Right? There's all kinds of possibilities, but we're looking right now at dehydration. Dehydration is effectively the loss of water to form an alkene. Okay, so you put this alcohol in the presence of acid, like sulfuric acid, something that the conjugate base is not a good nucleophile, because otherwise you're going to end up with a whole bunch of substitution as well, in addition to elimination. If I put HCl here, then the chloride ion comes and attacks the carbocation, and I end up with like an alkyl halide. I don't, in this case, trying to avoid substitution, I want to put some, a strong acid, something that is a poor nucleophile. So, okay, this picks up a hydrogen, good leaving group leaves, form a carbocation, then the solvent itself abstracts this, and you form the alkene. Now, you remember, of course, that best substrate for that would be tertiary, because your tertiary carbocation is your most stable, the one that is not going to rearrange. Also the fact that there's more than one possible product, right, in terms of elimination. So if I had, once I form a carbocation, I could eliminate this hydrogen and form a double bond here. And it depends on the groups that are here, right? Let me just, for now, make this a hydrogen, but potentially there will be a third possibility. But let me make this a hydrogen. So if my base, my solvent comes in and abstracts this hydrogen, I'm going to put these two electrons here, and then I would form this product. Conversely, if my solvent, whatever base, subtracts this hydrogen, then I'm gonna end up forming a double bond here. So I would have this carbon with two methyl groups, a double bond here, and then a CH, and then a CH3. Right? I mean, I can draw this out. Let's say CH and CH3. Right, you remember that? So the yellow one is involving these atoms, and you end up with this double bond here. This is involving these atoms, and you end up with this double bond here. All right. So, which is my major product? The more substituted one, right?
Yeah.
So, you look at your double bond, and you look at the fact that there's 3 carbons connected to this double bond, as opposed to only 1 carbon connected to this double bond. The size of the alkyl substituent doesn't matter, just how many positions in the double bond have alkyl substituents. So this is gonna be your major product, what we call the Zaitsev product. Okay, and this would be a minor product. And if I had had another carbon with another hydrogen here, then I would have had a third possibility. Okay, so anytime you have a carbocation, you need to worry about rearrangements, and in terms of eliminations, major and minor elimination products. Okay, so when you're looking, this is an equilibrium, right? I can put this alcohol in the presence of acid, make this into a good leaving group, have this leave form the carbocation and eliminate. That would be an elimination. Or I could put an alkene in the presence of acidic water and have this add across a double bond. That's an addition reaction, right? These are reverse reactions. What controls whether we're going mostly to the right or mostly to the left is the amount of water that you have. If I start with an alcohol in acid, try to have fairly, dry conditions. As soon as any water forms, I remove it. Then I'm going to drive equilibrium to the right. If conversely, I get an alkene and I put it in a sea of acidic water, then I'm pushing this in, and my whole equilibrium goes to the left. I remember Le Chatelier principle. How do you control an equilibrium? Well, you remove products, that drives equilibrium to the product, or you add more product that drives equilibrium towards the reactants. So in this particular case, your first step is the protonation of the OH, converting it into a good leaving group. Your second step is water leaving to form a carbocation. Your third step is elimination of this hydrogen to form this alkene double bond. They love this type of questions in PCATs and CATs. What is the first step in the elimination of water from an alcohol? First step is the protonation of your hydroxy. The type of question is just a classic question. All right. This type of elimination is occurring under acidic conditions. I could do the same thing under basic conditions. Rather than using H+, I'm using this reagent with a base, period. So when I'm giving you exams, typically my exams, there's going to be a lot of syntheses, right? Some of them, how do you make this? Some, it depends on, right? So if I were asking a reaction, here's this alcohol, and let's say PBr3 and sodium cyanide and whatever. So I could, for example, take away the reagents, leave these blank and ask you what are the reagents in here. I could have the reagents but take away this is a blank, and ask you what is the starting material and these reagents would give me this. I could, of course, make this a blank and ask you, given the starting material and this reagent, what is the product? I could have multiple steps. So there's going to be this, and this, and this, and then I give you a product, and maybe I give you a couple of the reagents and ask you to fill in the blanks, right? Or I could tell you, oh, here's this product, and I want you to make it from, well, let's say something more. Whatever. And I want you to make it from starting materials that have no more than 3 carbons. Something like that. Okay, so that's very open-ended. Any starting material you want. Go at it. Well, clearly you're going to need to make some carbon-carbon bonds. Since you have an alcohol, then maybe a Grignard would be good. Maybe we'll join this piece with this piece. So what starting materials would I be starting from? Blah, 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 blah. So these are all possible questions. But another type of question that you're going to have are mechanisms. So there's going to be at least one mechanism in the exam. And that mechanism, of course, involves each and every bond that you make and each and every bond that you break. Okay? That is what a mechanism implies. So you need to get used to writing mechanisms. So, for example, they're asking me, in a mechanism, I will give you everything. I'll give you the starting material, the reagents, the products, but you need to write step by step how this happens. So, let's look at that. You have so methyl cyclohexanol being converted to 1-methyl cyclohexene using phosphorus oxychloride and pyridine. Okay, so given this, we need to write a mechanism. Now, first of all, what type of reaction is this? an alcohol to an alkene. Some dehydration, an elimination reaction. In order to do an elimination reaction, I need to convert my OH into a good leaving group. In the past, we've converted it into a good leaving group by reacting with acid, by reacting with tosyl chloride, by reacting with PBr3. Now, PBr3 is kind of similar to this, or PCl3, except that I have this additional oxygen here. But let's do the same that we would have done with PCl3. Let's attack the phosphorus and kick out the chlorine. These arrows show the bond that is going to form between which electrons, which in this case is these two electrons, and what is the atom that is receiving those electrons. That's at the tip of the arrow. These two electrons are going to end up on this chlorine. Okay, so you show those curvy arrows, and then you're going to show what happens. So what happens in here is this oxygen has formed a bond to this phosphorus. This oxygen now has a positive charge, right? That is new. And then the chlorine is now a chloride ion. So let's draw that chlorine, which has gained these two electrons and is now a chloride ion. Now, you could write this as an E1 elimination or E2 elimination. Let's write it as an E2, just for the heck of it. Now, chloride ion is a pathetic base. Pyridine is a much better base, which is why they put the pyridine in here. Let's come in with the pyridine, attack this hydrogen, put these two electrons here, and kick this out. And that will give me this product, right? We remove this hydrogen, we put these two electrons here, and this is kicked out. Of course, in addition, what I'm going to have is this product and chloride ion. Right, but that would be a mechanism where step by step I show what's forming. Yeah.
Can you draw my pyridine larger?
It's like a benzene ring, but rather than having a carbon here, we have a nitrogen with two electrons, and those two electrons are basic.
What's attached to the phosphorus, the first one?
There's
the O and the
An
phosphorus.
oxygen and 3 chlorines is POCl3.
What's the
So in general, mechanisms are things that we go over. They are in your PowerPoints. They show step by step what's happening. But in the exam, you'll be given just this. You know, you'll be given this, the reagents, the product, and then you need to show me step by step what are the bonds that you're making, the bonds that you're breaking, clearly with this curved arrow showing me the movement of electrons. And then on the next picture, what are the new bonds that you formed, what are the bonds that broke, that type of thing. one by one, step by step. Yeah.
The double bond on the PCl3, well, it doesn't affect the reaction whatsoever. The double bond on the O.
So we can be a little bit more detailed and say, oh, okay, the oxygen takes the electrons, we go to this sort of intermediate, and then the electrons kick back in and kick out the chlorine. Sometimes we say this, okay, this attacks here, sends electrons up here, which comes right back and kicks this out. And that would be like a, all at once, this is what's happening. But yeah, effectively, you form the alkoxide ion and then the electrons kick in and kick out the chlorine. Yeah. All right. And when I give you homework, I have given you some of all of it, some mechanisms, some syntheses, some what is a reagent that is missing here, blah, 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 blah. All right, so start with this, write a mechanism for this reaction. What is the very first step? You have an alcohol, you have acid.
Protonation.
Protonation of the OH, right? Under those circumstances, that is always your first step, okay? You could you can write the full acid, sulfuric acid, but sulfuric acid is a strong acid. This is going to be present as hydrogen ions. Now, I could write the whole thing if you like to be that detailed, but the reality is that I'm perfectly happy to just write H+. Okay, but this attacks, either because you wrote H+ or you break this bond, okay? And now you have this with a positive charge. So this is a good leaving group. Let me write this like this. I could potentially have this leave, except that would give me a primary carbocation, and those things are not easy to form. So let's consider this as an substitution and elimination reactions. So if I do a substitution, my reagent that is going to come in, let me just, the reagent that will give me this product, my substitution product, is going to be what? is in ethanol, right? A second molecule of ethanol comes in. Attacks here, this leaves. Right now we have this, and then another molecule of ethanol. Let's call it a generic solvent molecule. Comes in, abstracts this hydrogen, and I end up with this product. That would give me this product. This is a substitution product. Then my other product is an elimination product. That solvent, that ethanol, could also come in here and abstract this hydrogen, put electrons here, and this gets to leave. So now I have a CH2 double bond CH2, right? And I've protonated this and whatnot. So these are my substitution and elimination products. And whenever you protonate an alcohol, you get both, unless it's a very weird circumstance in which you cannot have one or the other. So under most circumstances, you're gonna get both substitution and elimination. And that's competing reactions, right? So when you start with an alcohol, you can form, in addition to the alkene, you tend to form ethers as well, right? An ether is an oxygen with carbon on both sides. One because of substitution, one because of elimination. In general, low temperatures favor the ether, which is your substitution product. In general, high temperatures favor elimination. But usually both of them happen. But you can try to, let's say, favor elimination, but by heating to much higher temperatures. And here is what is happening. Protonate, if you can, you're going to form the carbocation. If not, you know, it's secondary, tertiary, if not. And then you eliminate or attack and form your product, substitution product. Of course, if you're going to form a carbocation, you can have rearrangements. So show me a mechanism for this product. In here, we're not talking about substitution at all. I just wanted to explain this rearranged product, elimination product. Right, you notice that in here I had two methyls here, well in here I have my methyls here. So this is clearly a rearranged product. So go ahead and show me the mechanism for that. So we have an alcohol, we have acid. My first step is protonation of the alcohol. That's my starting material. We pick up H plus, form this intermediate. In a mechanism, you're writing each and every step. This is a secondary carbon. Secondary carbons can form carbocations. And if we're going to have a rearrangement, we do need a carbocation. So let's make this good leaving group leave and form this secondary carbocation. Now, tertiary would be better than secondary. If I try to move one of these hydrogens, I go to another secondary. That's not going to do me any good. This carbon has no hydrogens to do a hydride shift, but it does have methyl groups, so not as good as a hydride shift, but if there is no possibility of a hydride shift, then we can do a methyl shift and shift one of these methyl groups over here, form this tertiary carbocation, and of course this was secondary, this is tertiary, so tertiary is better, that is a driving force to have this methyl shift. And then we need to eliminate, right? This carbon still has a hydrogen here, even though the line angle formulas is not showing it. So now a solvent, whatever solvent happens to be, I don't know what it is. In general, when you're at something like this, I just use a generic solvent, anything. This hydrogen is so incredibly acidic, alpha to a carbocation, anything will take it out. So I just write a generic solvent that comes, abstract this hydrogen, puts it here, and that gives you this elimination. Whatever the solvent happens to be.
So on a test, can we write that, or you want like an actual solvent?
So in here, it's obvious that the ethanol is serving both as a substrate and as a solvent. But if you had put S here, I'm happy with that. In here, I didn't really define this solvent. Maybe it is,
Can we use the water?
you know, no, you wouldn't use either anything with an OH because then you're going to have all kinds of other reactions. So, but you might be using some methyl chloride or whatever. But whatever the solvent happens to be. Okay.
Under what conditions can you do the methyl shift?
Under what conditions can I do what?
The methyl shift that you do.
You're trying to go to a more stable situation. So this right here is a secondary carbocation, like this one. This one here is a tertiary carbocation. That is going to something more stable. We're going from a secondary to a resonance stabilized secondary. That would be more stable. So yeah, if you just go from secondary to secondary, there's no driving force there. But going to a more stable situation, I'm not gonna hold you responsible for pinnacles. Pinnacles are very, very limited reactions that only work on one or two substrates. Because it needs to be a really, 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 really special substrate. One in which you basically cannot do hydride shifts, and the methyl shift that you do is from a carbon that has an OH, so that can then form carbon. Not responsible for pinnacles. You know, there's about 2 molecules that can do this in the whole world. We're just not going to look at that. This one is a little bit more common, not enormously, but a little bit more. So in chapter 8, of course, we had looked at ozonolysis of alkenes. We had looked at if you have an alkene and first you put some ozone to form this 5-membered ring intermediate, and second you put a reducing agent that breaks down this 5-membered ring intermediate into pieces, you effectively cleave this bond, put an oxygen here, and end up with these 2 products, right? We call that an oxidative cleavage. Now, there's an alternate way that I can get to the same products from the same starting material. But that involves 2 different steps, 2 different reactions. The first one, which we also saw in chapter 8, was to this double bond, let's add osmium tetroxide. Osmium tetroxide is a metal that has a bunch of oxygen, okay, that adds from the same side. And so initially you form again this 5-membered ring intermediate, but eventually you hydrolyze this, break, rearrange electrons or whatever, and you end up with this 1,2 diol. Okay, it's a cis 1,2 diol. We looked at that in chapter 8. The new reaction is this. Doing a cleavage, this 1,2 diol is also called a glycol. Okay, so if you put periodic acid on a glycol, you will end up finishing cleaving this bond. This becomes a double bond, and this becomes a double bond, and you form these 2 products. Basically what is happening, this is an acid, this picks up a hydrogen, this leaves, you form a carbocation, and then that accelerates and ends up cleaving this. Okay. Bottom line, the new reaction that we're learning here is you start with a 1,2 diol, a glycol, and when you put periodic acid, this cleaves, this forms a double bond, and this forms a double bond. That is the ultimate result of a periodic cleavage. So, for example, if I showed you this 1,2 glycol, and I say you put this in the presence of periodic acid, we're going to end up cleaving this, forming a double bond here, and forming a double bond here. So at the end of the day, I would have this right here and this right here. Or I could redraw this as a 5-membered ring, which this is, with an aldehyde here and an aldehyde here. That's effectively the product that you form. Don't worry about this too much. And I'm extremely unlikely to show you a periodic cleavage, periodic acid cleavage, so. Okay? So, in our search of reactions of alcohols, we now have a new reaction which involves making of an ester. Now, we're gonna look at the mechanism in glorious detail. But before we look at the mechanism, let me show you the ultimate reaction and what the products are. In what we call a Fischer esterification reaction, you're going to have a carboxylic acid you're going to have an alcohol you're going to put some acid and heat this. At the end of the day, this portion of the carboxylic acid combines with this portion of the alcohol, and we lose effectively water. Okay, you're going to combine this portion that is coming from the carboxylic acid with this portion that is coming from the alcohol. And then you're going to lose water. This is sort of like a simplistic thing. It doesn't occur like this. We're going to look at the individual steps. But when I give you a carboxylic acid and an alcohol, and I ask you what are the products, this new functional group that you made in here, we no longer have a carboxylic acid which has this acidic hydrogen here. This oxygen is now connected to an alkyl group. This is, as a functional group, an ester, right? Whenever you have a carbon double bond oxygen connected to some carbon, that is an ester functional group. So we call this an esterification reaction, forming an ester. Okay. So for any problem that I give you, right, if I tell you, show me the products of this esterification reaction. Okay, here's my carboxylic acid. We're going to lose OH from the carboxylic acid and hydrogen from the alcohol. And we're going to connect this carbonyl to this oxygen. So this piece is coming from the carboxylic acid. This piece is coming from the alcohol. And in the process, I lost water. Right. Those would be the products. Now, if we're thinking the reverse, the bond that I just made was this one, the one from the carbonyl carbon, between the carbonyl carbon and the oxygen, right? So if I look at this as an equilibrium, what I would be doing is adding water, OH here and hydrogen here, and that would give me these two starting materials. But this is an equilibrium that is controlled by the amount of water that I have. In the forward direction, this is an esterification or condensation. We are condensing these two organic molecules into one. In the reverse direction, we are adding water. This is a hydrolysis. We're adding water to an ester, breaking that ester bond into the carboxylic acid and the alcohol. So if I asked you which are the products of the hydrolysis of this, or which were the starting materials that I condensed together to give me this ester, you look at the ester, you add OH here and hydrogen here, and those are your starting materials here. Right, this with an OH, this carboxylic acid, and this alcohol. Right, when this carboxylic acid condenses with this alcohol, I get this ester. Or conversely, when this ester hydrolyzes, I get this carboxylic acid and this alcohol. So next time we're going to get started with this. We're going to look at the mechanism in a lot of detail and some variations of esterification reactions. And then we're going to get started with, oh, this is chapter 14. So chapter 14 looks at ethers and epoxides, and it's sort of like the continuation of this. So we're going to jump directly from 11 to 14, then have the first exam, and then go back to 12 and 15, which are spectroscopy, which is like a completely different thing. At the end of chapter 14.